Hello students, today we are going to deal about the next part of our topic is nothing but thermodynamic concept of selection of reducing agent using Elingham diagram. Before going to deal this thermodynamic concept of selection of reducing agent using the Elingham diagram, we come to know that we have to know that which are the thermodynamic terms, which are the thermodynamic concepts should be going to deal, should be going to act as a reducing agent in the Elingham diagram. No doubt we will deal about the Elingham diagram, but before that, why we need to study this thermodynamic concept? This thermodynamic concept it helps to predict the physiology of the reaction. Means what? Whether this particular reaction happening in the metallurgy, means conversion of oxides and again reduction of their oxides in the given set of condition or not. Means what? At a given temperature. Means what? At a given energy. How much amount of energy we have provided, how much amount of temperature we have provided, and in that case whether that given set of condition the particular reaction happening or not, that will be going to deal or that will be going to studied by this thermodynamic concept. And again in this thermodynamic concept we are having the various part or various concept, which are those. In that first concept is that is nothing but enthalpy. Okay, enthalpy, the definition or meaning of enthalpy, total heat content of the system. Okay, enthalpy is nothing but total heat content of the system or exchange of heat from system to the surrounding. Okay, that we call it as what? Enthalpy. Total heat content of the system or exchange of heat from system to surrounding, that we call it as what? Enthalpy. Heat can be denoted by the letter delta H. And as we know here, if any reaction is proceeded or if any reaction is going on, what will happen over there? There may be formation of one of the product and there may be one of the reactant itself. If total enthalpy, if you are studying, means total heat content, how much we are required for the formation of product from particular reactant. If you study here, that is product minus of reactant, if you did over there, what the enthalpy of a particular product, if enthalpy of product, if we will get greater than that of reactant, then that time what will happen? The enthalpy is always become positive. Okay, enthalpy value, whatever we will get, whichever we will get over here, that is positive, and at that case, the reaction happening over here, that is endothermic reaction. No doubt we will read that once again. The meaning of endothermic means what and exothermic means what. Okay. The next case, what will happen? If enthalpy of reactant is greater than that of product, in such case, vice versa will happen. What will happen? Here delta H value it will become negative in nature, and if delta H or total enthalpy, if it is become negative, we will get our reaction, that is exothermic reaction. Okay, so enthalpy, exchange of heat between system to surrounding or total heat content of the system. Okay, that we call it as an enthalpy denoted by the letter delta H. Okay, if delta H, total enthalpy, product minus of reactant, enthalpy of product minus enthalpy of reactant. If value of this delta H become negative, then we will get our reaction that is exothermic in nature, and the value of delta H is positive, the reaction which will be proceed over there, that is endothermic reaction. This is first parameter to study the thermodynamic concept of selection of reducing agent, that is nothing but what? Delta H, enthalpy. Now the second parameter which will be there, that is nothing but entropy. Okay, entropy is nothing but measurement of randomness of the system. Okay, how much that particular reaction is become randomly happen or randomness of the system, that we call it as a what? Entropy. That is randomness. Measurement of randomness of the system, that we call it as a what? Entropy. Or the word, another word is there, that is nothing but disorder. Measurement of disorder of the system, that we call it as a what? Entropy. Now the entropy can be denoted by the letter delta S. Okay, second term is there. Entropy can be denoted by the letter delta S. And as we know here, if delta S, which will be there, if it is positive, delta S of any reaction which will be there, if it is positive, then reaction which will be happen over there, that is a spontaneous reaction. And if delta S which will be there for any reaction, if it is negative, then reaction which will be happen, that is nothing but non-spontaneous reaction. If delta S is positive in nature and delta S is negative in nature, what will happen? Spontaneous and non-spontaneous reaction. That is about the entropy. Entropy is meaning what? Entropy is nothing but measurement of randomness or disorder. That we call it as a what? Entropy. Now the next term or next part which is there, that is nothing but third part which is there, that is nothing but Gibbs free energy. Gibbs free energy. The energy obtained, the name given from the scientist Willard Gibbs, that we call as Gibbs free energy. It is the difference between total enthalpy of the system and the product of absolute temperature and entropy. Here denoted by the letter delta G. Delta G, what I have told, Gibbs free energy denoted by the letter delta G, and it is Gibbs free energy is nothing but it is the difference between total enthalpy. It is the difference between total enthalpy of the system and product of absolute temperature and entropy. Okay, this is the Gibbs free energy equation for Gibbs free energy. What is the Gibbs free energy? It is the difference between enthalpy of the system and product of absolute temperature and entropy, that we call it as a Gibbs free energy, and it can be denoted by the letter delta G. And in this particular delta G, when it is positive in nature, the reaction is non-spontaneous in nature. Okay, the reaction is non-spontaneous in nature, and in this particular delta G, if it is negative, the reaction which will happen over there, that is spontaneous in nature. Spontaneous and non-spontaneous. Now let me tell here what is the meaning of this spontaneous, non-spontaneous, endothermic, exothermic, means what this all terms. Okay, then first of all I will tell about the meaning of this endothermic. What is the meaning of endothermic? Endothermic is nothing but in a reaction mixture, heat is absorbed. Just to see here, the meaning of endothermic and exothermic. Before going to deal endothermic and exothermic, let me tell you about the system means what, surrounding is what. Here in the universe, a particular area under thermodynamic study, that we call it as a system, separated by one of the boundary, imaginary line, that we call it as a boundary, and surrounding the area under thermodynamic study, that we call it as a surrounding. The system, a particular area in the universe under thermodynamic study, we call it as a system, which can be separated one of the imaginary line called it as a boundary, and except the system, the remaining part which will be there in the universe called as a surrounding. Got it? System, boundary, surrounding. Basic terms in the thermodynamics. Again, enthalpy, heat exchange from the system to the surrounding or from the surrounding to the system. Enthalpy, heat. Entropy, measurement of randomness or disorder from the system to the surrounding or surrounding to the system. Entropy, okay, denoted by the letter delta S. Gibbs free energy, it is nothing but it is a total difference between the enthalpy and product of absolute temperature and entropy, that we call it as a Gibbs free energy, denoted by the letter delta G. Okay, these are the three terms. Now, what is the meaning of endothermic? Here, consider one of the system here we took already in the endothermic reaction. Here, presence of water, and in this water I have added here KNO3, potassium nitrate. Okay, I have added in that steam, heat will be just get absorbed. Okay, heat will be just get absorbed, and a solution which will be there, our KNO3 and H2O, become cool in nature, and the reaction we used to call it as an endothermic reaction. Endo, inside, thermic, heat will be absorbed from the surrounding to the system, from the surrounding to the system, that we call it as an endothermic. Now let's take an example here, another one. Here I will take again H2O plus I will take NaOH. Here pellets of NaOH I will add. Then what will happen over here? Heat is evolved from the system to the surrounding. This is heat. It will just get evolved. It will go out. Then what will happen here? It will become hot in nature, and the reaction we call it as an exothermic. Exothermic heat. Okay, that we call it as an exothermic reaction. So what will happen over here actually? When water and NaOH become mixer, heat will just get evolved out. It will be just go in the surrounding, and whatever the solution we will get here, it is hot in nature, and that reaction we call it as an exothermic reaction. Let's take an example. You already know again urea in your home. If you urea added in your water, you will get the cooling mixture. The mixture will become cool in nature. Why? Because from the system to the surrounding, heat will just get absorbed. That we call it as an endothermic reaction. This is an exothermic reaction. Now the next part, spontaneous means what and non-spontaneous means what? Spontaneous, you may know the water from, isn't it? Water will fall from upside to the down. Is there any force required for that? Is there any engine? Is there any machine required? No. Water can be naturally fall from upside to the downside. It means no any extra force or no any added force is required to happen this thing. That the process we call it is as a spontaneous process. Naturally happening things that we call it as a spontaneous. Consider we want to flow water from the ground floor to the fourth floor. We need any machine, we need any engine, we need required water flow from the downside to the upside, we take water, isn't it? It means what extra force we require, extra added charge we require over here in this process. That process we call it as a non-spontaneous process. Means those processes can be happening naturally without any extra man force. That we call it as a spontaneous. Those things cannot be happening naturally. It requires the man force or any added force. That the process we call it as a what? Non-spontaneous process. I hope we understood the terms enthalpy, entropy and Gibbs III energy. These are the three terms we require in the thermodynamic concept for the selection of reducing agent in the Ellingham diagram. Now the next part we will going to deal, that is nothing but Ellingham diagram. What is the meaning of Ellingham diagram? Definition and the graph we will plot over there. Okay. So let's start the next term, Ellingham diagram. Next term we will going to deal, that is nothing but Ellingham diagram. I will tell the definition first and then I will explain the meaning of Ellingham diagram and then I will plot the graph over here. Okay, the Ellingham diagram, the definition, the plots obtained here, the plots obtained when, here I write the definition, the plots obtained when the plots we obtained, the plots obtained when the standard free energy changes, when the standard, I have already told, free energy gives free energy, the standard free energy changes The plots obtained when the standard free energy changes values. The standard free energy can be denoted by the letter delta G naught. Values plotted against the plots obtained when the standard free energy values obtained the free energy values are plotted against the temperature for the formation of 1 mole of oxides. For formation of oxides, the plots obtained when the standard free energy values plotted against the temperature for formation of oxides from corresponding metals using 1 mole of oxygen. Okay, then see the definition of equilibrium diagram. The plots obtained when the standard free energy values are plotted against the temperature for the formation of oxides, okay, from corresponding metals using 1 mole of oxygen. Just see here. Okay, these are our metals. Consider plus O2. What is going to form? Metal oxides is going to form. And for the formation of this particular metal oxides, how much amount of delta G value is required? Consider maybe it is of minus X kilojoule per mole. This is joule, kilojoule per mole. And here temperature, any temperature considered here minus T0 K. Kelvin in the form of Kelvin itself. Okay. Here equilibrium diagram, the plots obtained when the standard free energy values are plotted against the temperature for the formation of oxide from corresponding metals using 1 mole of oxygen. Here any metal we can use, but we are using here only 1 mole of oxygen. Here the formation of metal oxides, how much amount of delta G values and how much amount of temperature is required. The plot will be calculated, plotted over here. That we call it as a what? Equilibrium diagram. Now let's see the plot, how it can be. EHG is there and here AG is there. Okay, this is our plot. Now we will see characteristic features or simply equilibrium diagram. Features of equilibrium diagram one by one. First, we already know here these are the delta G values and this is the temperature. You can observe here easily all delta G values, the slopes which will be there of the delta G values move upward in the direction. Is it? Except this particular carbon, except this particular CO, all delta G values which are there, it can be moved upward. What is the first characteristics features of equilibrium diagram? We will going to deal over here. All delta G naught versus T lines are slope upward. I'll write here characteristics. Characters of equilibrium diagram. In that first character, all delta G naught versus T values, slopes which are there can be moved upward direction of delta G versus T values, slopes which are there can be moved upward direction except C. Delta G naught become less and less negative with increasing temperature. Here what will happen? It will become less and less negative as the increasing temperature. Here first characteristic what? All delta G naught versus T values slopes move upward, and delta G naught values which are there, values become more and more negative as increase in temperature. See here what will happen. See, consider this, all slopes of the elements can be moved in the upward direction as you increase the temperature. Here temperature, how it goes on increases, this delta G values which are become more and more negative in the nature. This is the first characteristic feature. What it tells, all delta G naught versus T value slopes are upward in the direction. No doubt, here delta G naught values become more and more negative as the increasing temperature. This slope I told because it is how it in temperature goes on increases over there. Here delta G's values become more and more negative in the nature. This is the first one. Now the second characteristic features, sudden change in the slope of graph at a particular temperature. There is a sudden change in the slope of graph. In the slope of graph, there is a sudden change in the slope of graph. Here can you observe, this is a sudden change in the slope of graph. There is a sudden change in the slope of graph at a particular temperature. At a particular temperature called as fusion point or boiling point. Here we can observe in that particular graph, here minus 200, in between 0 and here plus 200 is there, and here one of the graph just get changed here HG, isn't it, and here AG is there. Why it is changed at that particular temperature? The temperature is nothing but 356 degrees Celsius. It is going to change over there. At this point we call it as a what? Fusion point or boiling point. There is a sudden change in the slope of graph at a particular temperature called as fusion point or boiling point. For in case of HG, you can observe over here. Why there is a sudden change in the particular slope of graph? Because this particular point is a boiling point of the HG. At that stage, it starts to boil, so there is a sudden change in the slope of graph. Okay. When temperature, now third, when temperature is increased, what will happen over there? A point will reach there, a particular point will reach there, when temperature is raised, when temperature is increased, a point will reach there. Below of that particular point, all delta G values are negative in nature, and above of that point, all delta G values are positive in nature. Have you observed in that particular graph? When temperature is increased, a point will reach there. Below of that point, delta G values which are there, delta G naught values which are there, they are negative in nature, and above of that particular point, delta G values which are there, they are positive in nature. And when delta G values are negative in nature, all metal oxides which are there, when delta G values are negative in nature, all metal oxides which are there, they are stable in nature. Okay, and when above of that particular line delta G is positive, metal oxides which are there, they are unstable in nature. This is third one. First one, what I told, all delta G versus T slopes are upward in nature. Delta G values become more and more negative as they increase in temperature. Second one, sudden change in the slope of graph. That particular point we call this as inclusion point or boiling point. At a 356 degrees Celsius, this Hg will be just a sudden change. Why? Because this is the boiling point of the Hg mercury. Then a temperature increase, the point will reach below jet line. All delta G values are negative in nature and metal oxides are stable in nature. And above delta G, all values are positive in nature. Delta G values are positive in nature and metal oxides are unstable in nature. These are three. Now remaining. Now fourth one, just to see. At a normal temperature, fourth one, at a normal temperature, delta G value for aluminium. At a normal temperature, delta G value for Al is more negative as compared to, if you compare to, as compared to Cr. What I have told, this Cr and Al, if you have compared, delta G values is more negative for aluminium. Yes, at a normal temperature, delta G value for Al is more negative as compared to Cr. This indicates that aluminium has more affinity towards oxygen. So what the result is, so aluminium can be used as a reducing agent. So aluminium can be used as a reducing agent for Cr. What I have told, fourth one, at a normal temperature, delta G value which will be there for aluminium is more negative as compared to this particular Cr, chromium. So what it indicates, aluminium has more affinity towards the oxygen, so it can be easily formed the metal oxides. So aluminium can be used as a reducing agent for the Cr. So what is the reaction is 2Al plus Cr2O3, 2Al plus Cr2O3. What we will get here? Al2O3 plus what we will get our metal as it is 2Cr. This is our metal. Okay, what I have told, fourth one, at a normal temperature, delta G value for aluminium is more negative as compared to this chromium. So why? Aluminium has more affinity towards this oxygen. So aluminium can be used as a reducing agent for this chromium, and this is a particular reaction where delta G value which will become, it is more and more negative. This is fourth one. Now fifth one, at a higher temperature, delta G value for, at a higher temperature, delta G value for Ag2O and HgO, at a higher temperature, delta G value for Ag2O and HgO are positive in nature. Okay, at a higher temperature, delta G value for Ag2O and HgO positive in nature. Metal oxides can become unstable. Metal oxides of the Ag and Hg become unstable, so they can be thermally decomposed. So how it can be decomposed? Just to see here, Ag2O, when you heat this, what the element will going to form? 2Ag plus O, and HgO, when you heat this, 2Ag plus O, and HgO when you heat this, Hg plus O will going to form over there. Getting the term at a higher temperature, delta G values for Ag2O and this HGO. Please note, this will be move upside, and as we know here, delta G is here positive in nature. So if it is move in the upward direction, this Hg and Ag, the delta G values are become what? Positive in nature. And when I have already told, as the delta G values become positive, what will happen? Metal oxides become unstable and they can be thermally decomposed. Understood? Fourth and fifth point. At a normal temperature, delta G value for aluminum is more negative compared to CR, so aluminum can be used as a reducing agent for chromium. And fifth one, at a higher temperature, delta G value for Ag2 and HGO become positive and metal oxides become unstable in nature. So these two can be thermally decomposed. Okay, this is about fourth. Now fourth and fifth one. Now sixth one. Now sixth one. Let me tell. Lingham diagram for oxidation of carbon. Lingham diagram for oxidation of carbon. Lingham diagram for oxidation of carbon. Mainly two reactions are possible. Okay, mainly two reactions are possible, which are those C plus O2, CO2. Okay, C plus O2, CO2, 2C plus O2, CO. Consider this is a first reaction, this is a second reaction. So, for first reaction, number of here volume of O2 used, volume of O2 used is equal to volume of CO2 formed. For first reaction, volume of O2 used, volume of CO2 formed. Next, here what will happen? No change in the delta S. There is no change in the delta S. There is no any randomness in the reaction. There is no change in the disorder of the reaction. So, graph is a straight line. So, graph is straight line. Here what will happen? At which temperature that particular carbon is present? In between -200 to -400 it is present. Graph is straight line. I have told about this for first reaction. Now for second reaction. For second reaction, first point. Which is that first point for second reaction? Volume of 2CO produced. Here see, 2CO get produced, isn't it? For 1 O2. Volume of O2 is equal to volume of 2CO. Isn't it? 2CO produced for 1 O2. So what will happen here now? Delta S. Yes, delta S become positive in nature. And if this particular delta S become positive, the graph will be just moved here what? Downward. Isn't it? The graph will be moved downward. Slope of the graph will be moved downward. Just to see here -200 to -400. Here no doubt up to here straight line will come and up here downward. This is for second reaction. This is straight line for first reaction. 6.1 Lingham diagram for the carbon. For the oxidation of carbon, mainly two reactions are possible. Carbon to oxygen, CO2, carbon monoxide will form for first reaction. Volume of O2, how much amount of O2 produced, that much amount of CO2 will going to form. Volume of O2 produced, volume of CO2. Here no change in the delta S, means no change in the randomness, no change in the disorder. Reaction become as it is. So graph will move straight line. In the second case, volume of O2 produced, but here volume of 2 moles of CO2 produced. So delta S, yes, here disorder happened. So delta S become positive in nature, and so graph will move downward in the direction. This is sixth point. Now seventh point. what it is. This is about 6 point. Okay, what about the 7 point? In the equilibrium diagram, if any metal oxide reduced, in the equilibrium diagram, if any metal oxide reduced by other, I will take here example in the equilibrium diagram. If any metal oxide reduced, then oxides of other metal. I will take here example of aluminum can be reduced. If any metal oxide reduced by other metal oxide by other metal, I will take example here Mg. I will take here example of Mg. In the equilibrium diagram, if any metal oxide is reduced, then other metal, I will take Mg, it will lie above part. It will lie above part than the first. Okay, just see here reduction in the reaction plus aluminium. What is going to form over here now? Here the formation of plus 2Al. So this particular metal can be reduced by this Mg. So you can see here the metal which will be reduced by other, it will lie above that particular metal. So Mg is below of aluminium, isn't it? This is about the 7th point. Means if any metal reduced by the other metal, that particular metal lie above of the first metal. This Mg we have used for the reduction of this aluminium oxide. So this aluminium will be lie above of the Mg itself. Just to see, we have got metal aluminium as such, and we have used this Mg for the reduction of this aluminium, isn't it? We have used that particular metal. So this is about the 7th point. Now 8th point. From equilibrium diagram, it is possible. From equilibrium diagram, it is possible to predict. From equilibrium diagram, it is possible to predict the tendency of reduction. Possible to predict the tendency of reduction. From equilibrium diagram, it is possible to predict the tendency of reduction during metallurgy. From equilibrium diagram, it is possible to predict tendency of reduction during metallurgy. Okay, then 9th point which will be there here, the relative stability of metal oxides. The relative stability of metal oxides. The relative stability of metal oxides are nothing but Cr2O3, here MgO, Al2O3, Cr2O3, here Fe2O3, Fe2O3, and again HgO and AgO. From equilibrium diagram, the metal stability of metal oxides, MgO, Al2O3, it is more than that of Al, Al is more than that of Cr, Cr is more than that of ferrous, ferrous is more than that of Hg, and Hg is more than that of Ag. Okay, these are the 9 points. Let's we talk one by one once again. Okay, where should I explain this all point one by one? I will explain clearly. Once again, I will explain all the point. Just to see here, from first onwards, make part. Here, first point. Here, all delta G slopes are upward in the direction as increase the temperature. All delta G naught versus T slopes are upward as increase in temperature. Isn't it? This is first part. From the equilibrium diagram, we will predict all delta G naught versus T. Slopes of the oxide, formation of metal oxides are upward except Cu or carbon monoxide, and you can simply tell except carbon. This is first one. Second one which will be there. There is a sudden change in a particular slope of the graph. Sudden change in the slope of the graph. There is a sudden change in the slope of the graph. That point we call it as a fusion point or boiling point. Okay, I have took here example Hg, and here 356 degrees Celsius is a boiling point of Hg. First one, slopes are upward, all delta G naught versus T values which are there, slopes are upward, and except C as we increase the temperature. Second one, there is a sudden change in the slope of the graph, but that particular change we call this as a boiling point or fusion point, and here Hg we have put the example. This is second one. Now third one, a particular point will be reached. Okay, at that particular point, above delta G naught values are positive in nature, and below that line, all delta G naught values are negative in nature. And where delta G naught values are positive, all metal oxides are unstable. All metal oxides are unstable. Negative, all metal oxides are stable in nature. This is third one. Fourth one, at a normal temperature, aluminum has more affinity towards the oxygen as compared to this chromium. So aluminum can be used as an oxidizing agent for chromium. Here we have told aluminum has more affinity for oxygen. So aluminum can be used as an oxidizing agent for chromium. Here I will write 2Al plus Cr2O3 gives rise to Al2O3 plus 2Cr. This is fourth point. Now fifth point, what it tells the fifth point? It will tell at a higher temperature, as the temperature increases, here the value which are the Ag and Hg become unstable. Ag2O and HgO become unstable and thermally decomposed. No need of any oxides. They can be thermally decomposed. Fifth one. Sixth one, what it tells about the carbon. Two reaction we took. Here, in the one reaction, C, carbon which will be there, amount of oxygen we use, formation of CO2, and C, 2C plus O2, the formation of 2CO. These two reactions we took. And in the first reaction, the slope of the graph is straight line because delta S which will be there, it is negative in the first, and in the second, it is positive in nature because here the graph will be moved downward because 2 will be formed. Here no 2, here the moles of oxygen is moles of CO2 will go to form. Now seventh one, what it tells, if any reducing agent we are using, any oxidizing agent we are using, here we took example of Mg and Al. This Mg can be used for the oxidation of this same like this only, or you can take aluminum and chromium also. It will lie above that plate. Just as here for chromium we are using aluminum, so this chromium will lie above this particular aluminum. Or you can take here the example of Mg and Hg, so Mg and Al. So what will be there? C, and write here reaction. 3Mg plus 2Al2O3, 3Mg plus Al2O3, sorry, 2Mg plus Al2O3, what we are going to form? 2Mg plus Al2O3, what we are going to form? Mg2O3 plus 2Al. Okay, this is the next one, seventh one. Eighth one, it will be used to predict the will use to predict the tendency of reduction. Eighth point, tendency of reduction. And ninth point which will be there, this is the series of oxides which is going to form over here. The relative stability of metal oxides. The relative stability of metal oxides. Relative stability of metal oxide. This is all about this greenhouse diagram. They may ask the silent features of this greenhouse diagram. You are supposed to write this all 9 silent features. Nothing is there. Very easy part. Easily you can understand.